Okay, I think we're ready. We have got a few things to do today. One of them is we're going to look at some tuning settings that we didn't talk about last time. And then we'll do some modeling based on try to recreate a real part. So let's look at the printer over here. I need to, there we go, I can see better. So last time we made one of these. I don't think we printed this last time, or did we? I don't think we did. No, I think I'd already printed this. But we did some tuning. We tuned the E steps, so the extruder steps. We tuned that to make sure that the right amount of filament was coming out of the nozzle per the request of the G code, which the slicer, so we used Cura last time, the slicer has to calculate a volumetric flow amount, not necessarily rate. I guess there is a rate too, but the amount of filament that needs to flow out per layer. And it does that based on the nozzle diameter and the diameter of the filament that you're using, and the amount of steps that your feeder mechanism turns. Remember, these are stepper motors and they take incremental steps, not quite the same as a regular DC motor that just turns. These go to a certain number of steps. So maybe I want 200 steps, which would be, for this particular stepper motor, that would be one whole revolution of the stepper motor. And I want that many, however much filament is associated with 200 steps, I want that much filament to come out of the filament, out of the nozzle. And so that's roughly how the slicer tells the G code, which tells the printer how much filament to extrude per movement. In fact, if we look at some G code, I don't have any handy, do I? We'll look at some G code later on, not today necessarily, and talk about how the G code itself works. But we did that. We tuned our E steps. You should probably not have to do that on a new printer. You might want to. You might want to check, because that's the one thing that maybe there's a slightly different filament diameter that you're using or something. Maybe there's some reason that your flow out of your nozzle is not what it's supposed to be. So ours was, we printed this, and we could, actually we printed, that's what we printed. We printed the 9 squares to do a bed level, and a lot of them were not, they weren't fused together, so the little strips in one square weren't touching one another, and so we there's 2 reasons that could have, at least 2, there could be others, but there's at least 2 reasons that could be happening. One, the bed is too far away from the nozzle, so we did adjust a little bit on the screws that are at each corner that will raise and lower the bed, so we adjusted that a little bit. The other thing is that there's just not enough filament coming out, and so we went into, after we had adjusted the bed, we had adjusted the E steps, then we went into Cura and we just said, it still looks a little thin. We're going to bump up the flow rate by 5%. So we did that. There's another filament flow related parameter that you can tune, and this one, even on a new printer, you might want to tune. So what this is the way that the temperature for your hot end is controlled, and possibly your bed too, but the hot end is the one we're talking about right now, is called a PID tune. So PID is proportional, integral, and derivative. So that's what the PID stand for. And this is opposed to a control system that's called something like bang bang, where it's on or off. It's got 2 different states. So what you could imagine is, actually, let me get something that we can draw on here. Let's get this up. So now let's go to here. Let's get this on our screen a little better, something like that. And you could imagine you've got some desired set point right here. That's what you want. That's your set point. And for us, we're printing PLA, so maybe that's 205 Celsius. Maybe that's what we're trying to get to. And if you have the bang bang type of control system, so let's put, here's an axis, there's an axis. This will just be time, and this will be our temperature in Celsius. And our time will just be, we're not going to actually calculate anything, we'll call it seconds. So initially, we'll use blue, I guess, as our heat in the nozzle. So remember, there's a thermistor in the hot end. So if you remember, let's do this. Our hot end is a block of aluminum, and in there is a cartridge heater that we turn on and off. That's all we can do with it, really, is turn it on and off. And it heats up a block of aluminum. And there's also a, we'll make it much smaller, thermistor in there that's measuring the temperature of this aluminum. And then we also, you know, the nozzle, we'll make the, I don't have a brass color here, I have gray. That's not the same. There's our nozzle. So filament, make the filament green. Filament comes in here and it gets extruded out of the nozzle. So we've got heat generated here into this block of aluminum, and we're measuring the temperature in our thermistor. So this little guy is representing our thermistor. And we are using the two of those. So we're measuring temperature and we're applying heat energy. And we're using the combination of those to get our filament to our desired melting temperature. So in our case, we want it to be 205 degrees Celsius. So the bang bang, we'll make bang bang green. So this will be a bang bang control system. What it would do is it would notice that we're at 30, 25, you know, ambient temperature. So we'll put that down here somewhere. There's 30 C. And it's the thermistor recognizes that. You might even notice if you look at the screen of your printer when you turn it on, it's got some reading there for the hot end, and it's somewhere around 30, 27, 25, depending on where you've got your printer. It's probably indoors, so it's somewhere 25 to 30. And that is way below 205. So as soon as you send the signal to tell it that, hey, I want this thing to be 205 degrees Celsius, it's currently 30, it's going to turn on. And so it will turn on, and the temperature, it's probably going to ramp up. You know, the temperature is going to do something like, which way would it go? I think it would do something like this. And it's going to start heating up. The whole time the thermistor is measuring this, and the bang bang control system, I'm going to say that mine is set to, it turns off when it gets to 205. Now it might be a little smarter than that, and it's like, well, if I turn off at 200, then it'll go, it'll continue to heat for a little bit longer and go to 205. I want to say it turns off at 205. So it turns off right here. So it was on, now it's off because it reached the set point. It's going to keep heating, right? Newton's law of cooling will project, actually I guess that wouldn't be Newton's law of cooling, that would be the fact that it's still heating up, and we just turned it off. Then it reaches some maximum and it's going to just naturally start cooling off. That's Newton's law of cooling. And then it will get below the threshold point, turn back on, but it's still cool. It's got a while before it's going to keep back up. So it's going to do this sort of thing, constantly back and forth. And so it's going to have these overshoots and undershoots, and depending on how good or bad the control system, the bang bang control system is responding, you might have your printing at 215 degrees for a while, and then 190 degrees for a while, and it's going to bounce back and forth above and below your set point. So that's generally not what you want. So the PID tuning, I'm going to very much simplify it, but it takes into account the proportion. So how far away from your set point is it? It takes into account the integral. So in the past, how much heat energy have I stored up, more or less? So it's integrating over time, sort of. And then the derivative, so how fast am I currently changing? So, you know, the slope of the line it's currently at. So it takes into account those three things so that it will do faster ons and offs with predicting that, okay, I'm trying to get to 205 and I'm at 30. So it's going to start out the same, but it'll shut off way earlier so that it doesn't overshoot as much. And it's going to try to keep, you know, much closer to my set point much faster. So I don't have these big overshoots and undershoots. So the PID has three coefficients, one for proportion, one for integral, and one for derivative. And if you have those coefficients set wrong, then it's going to do even worse than the bang bang control system. It might overshoot way far. It may never get to your set point. It may have all these problems if I don't have those coefficients tuned correctly. And it'll still print. It just may have inconsistencies in reaching that set point. So what we want to do is we would like to tune those three coefficients. Now, fortunately, you don't have to manually do this. You can manually do this. You can go and figure them out yourselves. But pretty much every printer has a built-in PID tune. The firmware does. And so here in the canvas page, I've put a series of commands that you could do, or actually most of your printers on their control panel. So on here, there is a series helping me. There's a menu in here where you can PID tune the nozzle and oftentimes the bed too. The bed's not quite as big of a deal. What can happen, so the bed is interesting if it's not PID tuned. So let's go back. Oh, that's not it. Where did I put it? Down there. Let's go back to here. So the bed, imagine, this is very simplified case, but the bed is an aluminum sheet with some kind of build surface on top of it. And let's imagine that there are essentially two shapes that your bed might take. One is the cooled shape, we'll just make it flat. And then one is the heated shape, and we'll make it bowed up. You know, something like this. This is way more exaggerated than what it would really be. So it's got these two different states, one where it's not heating and one where it is heating. And if you have a bang bang control system on the bed, which a lot of them actually start out that way, and you have to go modify the firmware to turn PID on the bed. Nowadays, that's not quite as big of a problem. It used to be that the printer control boards had such limited amount of memory, you had to really select the stuff you wanted versus the stuff you didn't want. Now, it's not quite so much like that, and most printers will have PID control routines in their bed and their nozzle, in the firmware for them. So if I have these two states, and I have this bang bang where it's going on and off, trying to get to its set point, 50 degrees Celsius or whatever it is, then I'm printing something on top of here, and you know, sometimes I'm printing up here and sometimes I'm printing down here. And what'll happen is the print will come out, and let's say you're printing, this is what you're printing, a block, printing this block. And what you'll notice is that there'll be these little stripes in it. And the stripes will, all they'll be is places where the layers are closer together and places where the layers are further apart, depending on if the bed was in state 1 or state 2 of my little picture over here. Maybe this is state 1 is that one, and state 2 is the bowed one. Yours may not bow up, it could bow down, or it could flatten out when it's heated and be bowed when it's cooled, you know, it could be whatever. But I'm just imagining two different states here. And you'll notice these little bands in the surface of your print. So if you're noticing that, one thing that could be causing that is the non-PID, so the bang bang control system on your bed. Another thing that could control that is the lead screw. So if your Z-axis, it's back here, so you can't really see it, but you can see the very edge of it. Maybe no, it's behind the rail here. But the Z-axis that moves the gantry up and down, if it's wobbling, then that will also cause this banding in the surface of your print. So back to actual PID tuning. Let's see. So here's just a description of PI and D. If you're running Marlin for your firmware, which most people are, you're either probably running Marlin or Clipper. Clipper does have a different set of commands. I don't know that I should necessarily go through and show you these commands. Most printers actually have it built in to the screen, so you can go to the interface screen and do a PID tune there. Some newer printers, like the Bamboo and some of the newer Creality things, the little bit more expensive ones, they'll just do this like as part of their setup routine. They take like maybe 30 minutes and they go through a whole set of calibrations just automatically built in. So depending on what printer, you may or may not have, it may already be done. It may be something that you use code like this, Marlin. So here you would have to actually enter G code into the printer. We haven't really talked about how to enter G code other than loading a file. We'll talk about that later. But there is a routine built into the firmware, whatever you're using, that will do this PID tuning for you. I do have a little list here. These are the P, I, and D coefficients for some example output. These probably are not the ones you need. But there we go. When do you want to redo this? So if you change the hot end, so you switch from a brass nozzle to a hardened steel nozzle, or maybe you change the whole hot end, that would affect the PID tune on the hot end in particular. You put a new thermistor in, so maybe your thermistor, you want to print higher temperatures, so you need to switch out the thermistor. You need to do a PID tune. Maybe you just rerouted the fan, the cooling duct, the layer cooling fan, or maybe you've got a new fan for the hot end heat sink. That would affect PID tuning. This is the one that I'm most likely going to happen. You just put the printer in a different place. You went from an air-conditioned room out to your unair-conditioned garage, and the ambient temperature is way different. That's going to affect the ambient, cooling that could happen, the radiant, or maybe you got a fan that blows on it or whatever, an external fan. So anything like that could affect the ability for your control system to heat up the hot end, and that's a reason to do a PID tune. It takes, I don't know, this one here, this one's doing 8 cycles, so what that means is that it's E0 is the hot end, extruder, or well, it's not extruder. I think the E is for extruder here, but you can have E0, E1, E-1 for the bed. So that's the hot end, which most of our printers just have the one hot end. You have a set point. In this case, the example is 200 Celsius. I would probably do 205 because that's what I normally print PLA at. And then C is the count of how many ramp ups and cool downs do you want it to do. 8 is plenty. You can get by with 5 and still be okay. You could probably even do 3 and get some decent numbers, but it doesn't take that long. This is not 8 all the way from 200 back to ambient. It's from ambient to 200, and then it cools off maybe to 190 and then back to 200. So it's not like it has to cool all the way back down. So it doesn't take that long to run one of these PID tunes. Oh, let's see. This can help fix the bowing of the print on the bottom as the print progresses. It can. So if your bed has the bang bang tuning on it, so it's doing these two different states. If you do a PID tune on the bed, then it can minimize the two different states that the bed might be in. Usually, the bowing on the print as it's printing, usually what's happening there is the bed is not hot enough, and the part is the internal stresses as the part cools. So you have to heat it up to print it. So it's heated at 200 degrees or plus to print, but then it cools relatively rapidly. And those most materials, when they cool, they contract, and so the material itself is contracting, and it will pull. It want to pull inwards, which wants to peel the corners up. So a better way, if that's what I'm thinking, the bowing on the bottom of the print, usually that is a adhesion issue, and there are a couple of ways that you can address. One is this. So let's see this one. There are materials like this, which is this is layer near. And this is bed weld. So this particular one's for PLA, ABS, ASA, and PETG. Those are your main materials that you print with, other than TPU. But TPU sticks plenty well on its own. In fact, a lot of times with TPU, you have to do the opposite. You have to make some kind of release agent. But you can use something like this, which will help your part stick down better. You can make the part have extra surface area on the bottom so that it just has more gripping the bed. You certainly have to make sure that this surface is clean. So I usually clean before every print with IPA. So I have some over here. So some. Now this is the 91%. It doesn't have to be 91%, but the higher percentage, the stronger it is. But even the 70% stuff is fine for cleaning the bed anyway. So I usually use this. This is safe for the bed materials that you would use. Don't use acetone. Acetone, you think, oh, well, that's even a stronger chemical for removing stuff. But acetone will eat away. Like this is a PEI sheet, so I don't remember what PEI stands for, but it's a material that does help your print stick down better. But acetone will eat this surface away. So use something like this. The first time that before you do this, just use hot soapy water and clean this surface really well. Usually, most of the bowing, you can use glue stick. I see somebody. There's probably a glue stick sitting around here somewhere. I don't see one right now, but glue stick. Brim is also. Let's talk about brim. Let me open up Cura here. Where did it go? I have lost my. That's interesting. There we go. Cura is not running, so Cura takes a while to start going for me. So I'll start it and we'll get back to it. So all of those things, usually adhesion. Now I have had one of these beds. I'll just warn you about this. I've had one of these kind of beds, so the magnetic ones that are just held down with a sheet magnet, kind of like the flexible refrigerator magnet stuff. I've had one of these where I printed a large area, and I used, I don't remember what I used. I might have used some of this stuff, but it stuck to the bed, no problem. The problem is that the material, the PLA or whatever I was using, still wants to contract and warp. So what it ended up doing is it peeled up the corners of the print bed. Because it was such a large area that was trying to warp and trying to contract and warp. And so it didn't come loose from the bed, it just peeled the bed up. So if you're printing a really large area and you think it's going to warp, and you're using one of these magnetic beds that, you know, they're held down, but they're not super strong, then you probably want to use some binder clips, like one on the middle or the corners or somewhere, because I have had large prints just stick to the bed and peel the bed up when they want to contract. Let's see if Cura opened. Yes, it did. All right. So you mentioned a brim. Let's put some part in here. Let's add, let's just do this. So here's our little part. Now this part probably wouldn't warp, it's tiny. But in here, you've got build plate adhesion. Now I normally use a skirt. A skirt does not do anything for build plate adhesion. Let me show you what it does. So this little outer track around everything, that's the skirt. And what it does is it gives you a few minute, seconds, depending on how big of a skirt it is, to kind of do some last minute adjusting on your print. So maybe you're noticing that it's printing over here and it's really thin. You can go and adjust this knob to raise that bed up or lower it down, whichever you think it needs, before the actual print starts. So skirt doesn't actually help the part here adhere to the bed, but it will help just give you some time to adjust things before you start printing. A raft, well, you said brim, so let's do brim. A brim is similar, except it's actually attached to the part. So what it does is now, instead of just this little rectangle or square being stuck to the bed, all of this is stuck to the bed. So it actually gives more area sticking to the bed to try and hold those corners down. So a brim, like you mentioned, could help with holding corners down. The other one is a raft. This one is kind of my last resort. It looks like a brim, except that it's multiple layers thick. So this one is what, 4 layers thick. The only time I bother using a raft is if I'm printing really tiny pieces. So if I do a brim on really tiny pieces, it's hard to remove. It's actually connected to the part, and you have to cut it away, and the piece is really tiny. But if I'm printing really small things and I don't think they have enough area to stick down on their own, then I will print a raft. And a raft is not connected to the part. The part is actually sitting on top of the raft. So if you have a warped bed or a bad spot in your bed or something like that, you can print a raft to kind of cover over that spot, and then your part prints on top of that raft. The downside is that it takes significantly longer. So 27 minutes versus, let's see if we did just the skirt that I normally would do. Well, only 5 minutes longer in this case. But if the parts are large, then those rafts can start taking 20 or 30 minutes of your print time just to print something you're going to throw away. So I don't use a raft very often. It's kind of the last resort. But I almost always do use a skirt here, just to have a visual of it's going to print in this area and it looks like the filament is extruding well. And if I think the part is going to peel up, or it just doesn't have enough area but it's not tiny, then I'll use a brim. Those, and all the time, make sure you are cleaning the bed. Maybe you want to use some of this sort of thing here. If you do get some of this, make sure that it does work with your material. Some of them are specific to certain materials. Or the glue stick will work. Another one that I use often is, let me go get it. I will use this purple can of Aquanet hairspray. I'll use that one. I like it a little bit more than the glue stick because it at least goes on smooth. It still adds a little bit of a layer that's attached to your part that you may not want, but sometimes the glue stick doesn't smooth out very well. If you are going to use glue stick, wait until your bed is 30, 40 degrees Celsius, and then put the glue stick on, and it'll level out a little bit better versus being a little bit lumpy. All right. So that PID tune, yes, it can help a little bit with what you're describing. It really is more, well, the nozzle PID tune is important for the flow rate. The bed PID tune is kind of, if you're having those issues I was describing with something like, not that, these little stripes in the side of your print, that could be fixed with a bed PID tune. All right, I don't see any other questions over there. All right, so PID tune is one thing that you can do pretty easily. You probably don't even have to use the commands that I wrote out. That's if you're actually writing G-code commands straight to the printer. We'll do that sometime just so you can see it happen. Most of the time you can just do that in the menu on your screen here. It would be in like advanced settings or something like that, or configuration, and there will be a extruder PID tune in the temperature menu. All right, so we did make this based off of this, actually, well, that I guess, and we did that by taking a overhead picture of it and dropping it into Fusion and then extruding it 6 millimeters, and we printed it out. So we did that. I wanted to do a similar thing, but working with a little bit more complicated geometry and a little bit more thought about, hey, I want to print this thing, so that means some of my dimensions need to be constrained to whatever layer thickness I'm going to do. So what we're doing now is I have this guy down here. This is the G.I. Joe X30 right there, something. Got this off of eBay, and it's missing most of its parts. So we're going to use a lot of different techniques to replace most of these parts. So one that it's missing is this is based on the X29. So let's see, based on this plane, sort of. This is a real test plane from Grumman, the X29. The G.I. Joe one's called the X30. There's also a Russian plane that's similar, except this plane came out after the G.I. Joe one did. So I don't think the toy is based on this plane, because this plane's actually newer. But these are just the forward swept wing planes, and this is what we're trying to make ours back into, something like this, although ours is missing most of its parts. So one of the pieces it's missing is these. Now I do have one. So I have this one. I can't get it in there right now, but they go there. And so what we're going to do, since I have one missile, one of these. I don't have this cover. I don't have this. I'm missing the front landing gear. What else are we missing? Oh, there's two little wings here. I don't have either one of those. So there's a bunch of pieces that we're missing. This one, at least, we have one of. So if we can copy this, we can print new ones. We could keep this one, I guess, but we'll just print two new ones to match. So what I've done so far is I found my little grid, and I lined it up here and took an overhead picture just like we did with this guy. So we did the same thing as that. And what we're going to do is take that into Fusion, and this one, let's see if you can tell, it has some panel lines, some little grooves in it, and it's pretty thin. So I measured the thickness, and it's a little bit variable, but it averages to about 2.1 millimeters thick. And I do want to try to put these little lines indented into the surface. So when we start trying to figure that out, trying to find where I put OneNote, there we go. When we start trying to figure that out, I've got, this is kind of be my rough side view of one of these things. So there's going to be some indentions on both sides because it does have those panel lines on both sides. And I need this dimension to match pretty close because it has to slot into a little groove that's on the body of the plane. Pretty close to 2.1 millimeters. So what I need is I want this to be like one layer. Same thing with this. I want that thickness to be one layer. So I've got to come up with a layer thickness that's printable that will give me 2.1 millimeters. So I need something that evenly divides into 2.1 and then that is not so thin or thick that I can't print it. So I could do 0.3 millimeters and then have 7 layers, right? And the indentions would be 0.3 millimeters deep. So that's a bit much, but we could do that. So that's one option. Is option 1, layer equals 0.3 millimeters. Oops, I covered that up. We'll move it over here. If I can, there we go. The next obvious one then, if 0.3 millimeters works, then option 2, layer equals 0.15 millimeters. So one of those two will work and give me an even number of layers. So when you're printing and you know what layer thickness you're going to use and you're designing a part for that layer thickness, then you have to start thinking about, well, if I want these indentions, then they need to be an even increment of some layer thickness. So either one layer or 2 layers. If it gets into half a layer, then they may not print. You know, the slicer may ignore them, and they're not even, you spend all that time modeling them and they don't even get printed. So I want them to at least be one whole layer. And so I don't think I want just 7 layers. That would be a faster print, but I don't think this print's going to be terribly long anyway. But I think I'll go with 0.15 millimeters. That's a little bit thinner than I would normally like to print. I would rather print at 0.3 millimeters, but I just think that that's probably going to be a little bit too coarse. The other thing is the material. So what material should we use for this? These little wings, you know, they're going to have to insert. So this little rib right here inserts into this slot, these slots here. So it has to be rigid enough that it can insert into those slots, but it also has to be a little bit flexible. So you know, got to be a little flexible. I plan to print these laying down. That slot is at an angle. You can kind of see there it's kicked. Where can I get it? There we go. That slot is at an angle, and I'm just going to print it up. Maybe some support material under it if I need it. Typically, if this angle, you know, if that angle is 45 degrees or steeper, more vertical, then you don't need support material for most printers, or actually really for any printers. But if it's shallower than 45 degrees, you know, it's more horizontal, then you might start needing some support material. This is not a 45 degree angle. It's more like a 60 degree angle, I think. Or 60 or 70 degree angle. Maybe we'll just make it 45. It doesn't actually matter. But I plan to print it just face down, so that will give one side with that texture, the textured surface of the bed that I'm using. And then the top side, there is a command that we can do that will help with flat surfaces that are on the top of your print. and that's called ironing. So enable ironing. What this will do is, and we can, well, we can, any flat surface or only the highest layer. In this case, the highest layer wouldn't work because the highest layer is going to be one of these, kind of like this edge. But if we turn on ironing, then the flat surfaces will be ironed with the nozzle, the tip of the nozzle. It'll be heated up and kind of drug across the surface like an iron would be. It can extrude a little bit of material if you want it to. Actually, this one, flow. So 10% extrusion just to have a little bit of extra material on top. And it works pretty well to flatten out the flat surfaces that are on top of a print. They have to be parallel to the bed, for them to be flat. There is a non-planar ironing, but Cura doesn't have that. So we can try that to help smooth out the very top surface of the wing if it looks like it's going to need it. All right, so how are we going to make this thing? I think we're going to go with a 0.15 millimeter layer thickness, 2.1 millimeters thick, and we're going to try these little insets, and we're going to try to create that little kick up. I don't know if we can do that in the amount of time we have, but we'll see how far we get. So I'm back in Fusion. I did already take the picture here, so I'm going to insert a canvas, which is their word for pictures usually. I have it right here. Open. I'm going to put it on the top here, and let's see if I can get it. I really would like for this line, so I didn't, my picture is not perfectly straight. I'd like for my grid to be along the red axis here. So I'd kind of like to get that straightened out. Let's see if I can zoom in closer. There we go. Let's see. Maybe one. That looks pretty square, doesn't it? Let's see if we can get the. That looks pretty square. So we'll call it, call it that. All right. Now it's my picture. Whoops, the dogs decided something's important. The picture's crooked, but the part is straight, is what I want. Now I need to scale it. So this is why I use the little grid. So remember, we can open that canvas, right click and calibrate, and I will just, this is a 1-inch grid. So there's 1, 2, 3, 4, 5, to there will be 6 inches. And then it made it much larger. Now this part is very similar to what we did last time. So I will probably simplify this because we don't need to spend a whole bunch of time doing this part, but I'll show you the main steps. So there's a line, and let's create a spline. I'm increasing the size of this little nub on the end just because I'm going to work on it later. I'm just trying to get reasonable amounts of control points here. That looks pretty good. Close enough. We could get really picky, we're off some there because I put this little extra, whoops. We can maybe do a little bit like that. Okay. I did not include that little piece because that's the part that angles up. So I'm not including that yet anyway. All right, so we'll finish that and let's just extrude that thing. The 2.1 millimeters. So already we've got this looking decent. Now my actual part has a sort of rounded over edge all around here and back here and on the top here. So we'll see if we can do that with a fillet of that was 2.1 millimeters thick. So let's make this 1 millimeter, and that's pretty close. I mean, that looks okay. Okay, so there is our rounded over part. Now let's try to put some of those little grid lines in there. I won't do all of them just to save some time, but how I'm going to do this is create a sketch on the top surface here. That'll be fine, and we will use a line, and we'll just trace over. Let me see where these lines are. It's kind of hard to see them. All right, that goes all the way down to, it connects with there. Let's actually start up here. So there's one, and there's one. It made those parallel automatically, so that's good. We will drag that guy out. We'll trim this, so there's a little trim. We can just make it in right at that point. And then let's do these two lines. Looks like I missed a little bit. That's fine. Oh, also, it looks like I did some weird jag. Let's erase that one. And let's pull that one down to there. And then we will trim those pieces off. All right, so now I've got to think about how wide do I want this little indentation to be. My nozzle I'm using on this printer is 0.4 millimeters wide, and these are indentions though, so actually indented grooves can be more narrow than the nozzle. If they were raised, then they have to at least, they would be better off if they were a increment of the nozzle diameter, but since these are indented, then I can actually make them more narrow. But I think 1 millimeter is a reasonable size for these. So what I'll do is I will just offset these. I'll offset them 0.5 millimeter in either direction, and I'll offset this one too. Oh, and well, I guess I have to, that's apparently not the same line. Hold up. Oh, that's weird. Let's fix that. So connect those together. Didn't want to connect all those together. There we go. Okay, and now I'll just delete the inside one. Oh, all of the inside ones, since that one's separate pieces for some reason. Oh, and look, I didn't get rid of that one. And these are, since they're offset, they're not quite right, so we need to trim these guys off and then connect them. Sorry, it's still not connected somewhere. Let's, oh, over here. Oh, whoops, I trimmed the wrong one. That one. All right, so now I can select that one. Let's get this guy and trim. All right, that's still not somewhere. Oh, over here. All right. I'm just using L and T for line and trim. All right, so now I can select those separately. All right, so there are more lines on here. We're just going to do these because I don't want to spend the whole day doing this little stuff. So we will select those and we will extrude them. We decided that we were going to do one layer. So we're going to extrude them into the thing. So they're actually going to be a cut. And we will extrude them negative 0.15 millimeters. And then now I've got little indentions there. Now I want them on this side too, right? Not just that side. They're on both sides. So what I can do for that is should be able to, where's my origin? I should be able to draw, oh, let's do a, let's go back to our sketch that has those in there. And let's copy them. Oh, not that part though. I just want these. And I should have joined those, but I didn't. Okay, got those. So Control C to copy those. We can go out of the sketch now. And now we need to, what do we need to do? We need to create a new sketch. And we need to create it on this surface. And we can paste, Control V. Now they're on the wrong side, so we have to mirror them. And I could select them, except I don't want, why won't it let me? I have to do it a little bit manually, I suppose. All right, so there we have selected them. There is a mirror. I've got those. Mirror line will be the whatever axis that is. I've lost the z-axis. Now they're over there. We can get rid of these. We don't need these anymore. Looks like I had some redundant lines in there maybe. All right, now let's go check and make sure these are, all right, so they're not quite, yeah, they're not quite sealed up. Let's fix that. That one's still not quite, must be down here. Yes. There's probably an extend that I could use. All right, that one's fixed. Okay, and then we do the same thing. Oh, whoa, except I flip this all around. All right, so we'll finish the sketch. And then we will get these two. We will extrude them. They're going to be a cut. And they will go negative 0.15 millimeters. So, and we can turn that canvas off to see what we've done. So there's the little wing. We could make more of those lines if we wanted to. We've got the, you know, the edge more or less rounded over. We just don't have our angle. So we want this, when it's on the plane, to be something like that. So we need that angle coming out straight down from this view, which is not any of these views. So what I need to do is I need to create some reference planes. So construct, let's first do I guess, and I don't know which I should do first. Maybe I could do a plane at an angle. Let's do an offset plane, I think. And we will take that plane and we'll, let's see, to object, let's go down Oh, will not let me offset it to there. I want to select that. I guess I could manually do it. I should have measured how far that was going to be. I didn't actually do that. I think maybe maybe that's not the best way. Let's see, plane at angle. Let's see, we're going to reference that. You can't see what I'm doing. I'm going to reference that, and then let's see. I want it to sit something like that. So 20 degrees maybe, or negative 20, I guess. That looks about right. Oh, you know what I could do is I could just move this. Move bodies that. We're gonna let's move from point to point. So let's move there to there. Now, yeah, that'll work. All right. Now we've got our slanted plane lined up with that bottom piece there. Now I think we can draw a rectangle. So let's create a plane, or create a sketch on our new plane. And we need to reference these lines. That line is on that plane, but this one is not. So I'm going to, where's it at? Right click. No, I will create, I will include these projections. So I'll project that line, that line, that line, and that line onto the plane that we are currently working on. They turn purple. So now I can actually select those lines, or at least reference them. So I can create a line that got some weirdness there. That's okay. Goes from there to here-ish. It doesn't go all the way to the end. In fact, the distance here to here is 5 millimeters. I already measured that. So like that. And then let's create another line from that end point. Whoa, should not have done that. To there. And let's also get it 5 millimeters. And then we can connect these to there. And there to there. We have a finished sketch. And now I've got this little box. I can extrude that. I can extrude it, let's see, the distance I can make to object. So I can just extrude it up to there so it fills in that gap. And then that's okay. Now I need to extrude it downwards. So there, extrude, I think it's 3 millimeters. Not 30. That would be too much. Actually, let's do less than 3. That looks, well, no, it'll be all right. 3 millimeters, and then to help make it fit into the actual slot, I'm going to chamfer it, and we'll chamfer it maybe 1 millimeter. Nope, less than 1 millimeter. There we go. Just to give it a little bit of a, a edge that will make it easier to go in that slot. And there's our part. So we've got our little angle on there. Now, is that the right angle? I don't know. I didn't measure that. It actually looks like we could use a little bit more angle. We did 20 degrees, but maybe we need more than that. We've got our panel lines in there. We can right click on this guy, save as a mesh, and STL binary is fine. Unit, we built it in millimeters. We will save this as this is the X30 wing, and it's going to go in my downloads folder. Okay. Now we can go over to Cura, and we can get rid of our little test cube thing, and we can add in our X30 wing. It was in downloads. There it is. Now we don't want to print it standing up like this. We could, but the layer lines would be in the direction that it'd be really easy to snap it into a, across a layer. So I want to lay it on this surface. So I've got rotate, lay flat on. That's not the surface I want to lay it flat on. Oh, I guess I could just rotate it. Let's rotate it by oh, it won't let me. Can I not put the number in? Oh, I can turn off snap rotation. I actually want to put the number though. There, I thought. Oh, select a face to align. That's what I want to do. I want to align it with this face, if it'll let me select it. There, it finally did it. All right, so it took a while. I think this overhang, you can see it's red right there. That's Cura telling me that that overhang is too shallow to print without supports. So I would just turn on supports. So now we need, let's go back out of here. Our layer height, we decided it was going to be 0.15 millimeters. The first time we print, we'll print in 2 walls. This one's not going to have that many walls anyway, unless you wanted it totally solid, and then it would be a lot of walls. We'll do 2 top and 2. Actually, let's do extra top and bottom. So we have 14 layers total. So let's do 3 and 3. Our infill density, I would probably just use a grid. That's fine. Now, if I were printing this in PETG, it has to print a lot hotter than 205 degrees, so more like 225. The first time I print it, I would probably just print it in PLA, so 205 is fine, with a build plate of 50. For PETG, I would want to print at maybe 225 and the build plate around 80. We'll practice with some PLA first and make sure the part's actually working, and then we'll print it in PETG. I have way more PLA than I do PETG. 75 millimeters per second print speed. That's kind of fast, but probably okay for this part. Since it is PLA, we will have print cooling. With PETG, this cooling actually hurts it. So PETG, you usually run 50% print cooling for fan speed, or at least I usually do. So PETG without any cooling is super strong, but it's a little bit bumpy, like the surface is not very nice. So you usually have to have some cooling for PETG. And if you have 100% cooling, then it looks fine, but the layer adhesion is really bad. And it just crumbles, like the layers separate very easily. So with PETG, you probably want, I usually do 50% cooling. But this first one's going to be PLA, even though I want the final ones in PETG. I probably do need support. I probably don't want a tree support. Tree supports are when you have more organic shapes, or maybe you're trying to reach around the part and support something higher up. Since this is just going to be a little ledge, I would just do a normal support, touching the build plate only. Now, what I don't want is I don't want it to print supports in my little grooves here. So I do need to make sure it's not doing that. If it is, then we may have to do this support blocker. All right, so let's slice and see what we get here. All right, you always preview. So is it, I don't think it's doing any support in my little grooves here. I think it left them alone. All right, let's look at our layer. There's our little supports there. That's not much. Let's look at the layer by layer view. So you can kind of see this weird pattern on top that we don't normally have. That's the ironing that we turned on. Now for some reason it says I have 19 layers. Not sure where it came up with that. So, oh, because, oh yeah, we do have more layers because we have the little kicked up thing there. There's 14 layers of the actual thing. So I've got that one layer with the little panel lines in it. There's my grid. There's my two walls, which if I think it's not going to be strong enough, I can add more walls. There's a solid bottom. There's the bottom with the grooves in it, and it did not put any support in those grooves, so that's fine. And then that little rail is the support for the little tab that kicks up. All right, so I think, and it would take an hour and 11 minutes. So I think that's a reasonable one to try to print. We would print it in PLA. Now I just noticed something on my printer. When we left it, it had this filament in it, but now there's none here. So this happens relatively often with some of the more brittle or older filament. So it will just snap. So if you have your filament and it's just snapping like this, then there's a good chance it's not going to print very well. So it has gotten moisture in it. This is PLA. Yeah, this is PLA. But even PLA, particularly where we live with 70% average humidity, even it will absorb moisture. And it looks like maybe back here it's not so bad. It's actually bending without snapping. But that part that's just snapping, like these little pieces here, that has too much moisture in it to print very well. You can either try drying it out or just snapping off the bad, bad pieces and getting to some of the more flexible stuff. Like this would print okay. I don't think I'm going to print this in yellow, though. I'll print it in some more, maybe black. Maybe I have a black PLA I can print it in. We don't have time to print it right now. We have 8 minutes. So I will print this. Also, we've made one of these. We can just mirror it to make the other one. So we don't have to go model the other one. I might go back and, try to make the angle steeper and all that, but I'll go ahead and print this one. There's some more panel lines we can add, but I'll print this so we can see what it's going to look like on the jet, if it's going to fit, or we need to adjust any thickness or anything. But that one is, we still took kind of the same approach where we did an overhead picture of our part. And we did add some more details. We'd added the panel lines. We added this little ridge to make it angled when it's in the plane. And we did a little bit more complicated modeling. Some of these other parts, like it doesn't have this cover. It doesn't have a screen up here. It's missing the whole front landing gear, including the tires. So there's a lot of other things that we're going to have to do that aren't going to be just take a picture and trace it. So we're going to have to do a little bit more complicated modeling on some of these others. And we'll work our way up to that. I think next maybe we'll try making these. These are not too complicated. They're very symmetric. But some of these other parts are going to require some scanning. I would do a couple of different types of scanning, to not for any particular reason other than to show you different types of scanning. But maybe we'll use photogrammetry for this, and maybe like a laser scanner type for replacing the wind screen. So the front landing gear will probably just have to, I don't know. We'll have to find some pictures of what it's supposed to look like, because I don't have it at all. All right, so next time, Wednesday, I'm not 100% sure what we'll do on Wednesday because I'm running a camp, or helping run a camp, and it starts during class time, so I may have to put a video that you can just watch. It'll premiere, but it won't be actually live. I'm not sure exactly how we'll handle Wednesday, is what I'm saying. But I'll figure it out, and I'll let you know. All right, I will see you all soon. Maybe Wednesday. I might be recorded